Hello, everybody. Welcome to this webcast on check valve modeling in Pipe 2012. I know some of you are familiar with my work and presentation, and for those who are new to this, welcome again. Over the years, we had several questions on how to model check valves in general, and also had several requests on the new features that the users wanted. And we introduced some of them in our new release, Pipe 2012, which is available for download right now from KYPipe website. And I strongly encourage you to do so. And, the main intention of this webcast is to describe some of these new features and also talk about the check valve modeling in general. And obviously, the 1 hour is not sufficient for this being a huge topic, and 1 hour is not sufficient. I encourage you to write me directly at srini@kypipe.com. I will try to answer as many questions. I will try to compile the questions into groups and then try to send the answers to everybody over the email. Before I begin, I'd like to thank you, all of you, for your participation in this webcast, and also the continued support for the KYPipe activity. I know some of you are overseas. It's very late for you, and despite the time difference, you wanted to participate, and I really appreciate that. So let's begin. This slide shows the kind of outline we're going to talk about today. After the introduction, I will briefly discuss various types of check valves and their dynamic characteristics. And this is the kind of information that you would get from some of the reputed manufacturers who have taken efforts to, generate that non-dimensional characteristics data. Not everybody. I was not able to get this kind of data from everybody, but some of them do provide that, and it is very important. So we'll discuss that a little bit. And then we'll talk about check valve modeling options in Pipe 2012 and spend quite a bit of time on the new check valve element that we introduced in the Pipe 2000 software. Before we begin, I want to for some of you overseas, the check valve is also referred to as, non-return valve in some parts of the world, reflux valve, zero velocity valves. Certain manufacturers of surge suppression devices, market the check valves as zero velocity valves, but they are basically check valves, and we talk about them briefly as well. They're also referred to as back pressure valves, and I'm sure there are many other ways, the check valve is referred to different parts of the world. But the basic, the requirement or the basic function of this check valve is to prevent flow reversal in the pipeline, and primarily in the pump stations. When there is a pump trip, when you're pumping water uphill, when there is a pump trip, after the water column slows down, the reverse hydraulic rail line will force the water column to move backwards. And if it is not prevented, if that reverse flow is not prevented, it may potentially damage the pump, motors, etc., and also drain the pipeline. Which is, filling of the pipeline is a very tedious process, and you don't want to keep draining the pipeline. And that's the main purpose of the check valve. But check valves are used several different places. We will discuss them as well. So the primary purpose of the check valve is to prevent reverse flow. And because of that, the preventing the reverse flow means change in the flow rate or change in the velocity. And that has some, even though it is supposed to protect the pipeline, sometimes if it is not designed properly, if it is not sized properly, it can have a detrimental effect on the pump station piping. So let's talk about what causes pressure surges in the pipeline systems in the first place? There are many reasons. We can say pump trip, pump startup, pump shutdown, valve closure, pump, the pipe burst. There are many, many reasons why there could be pressure surges in the pipeline systems, but I can summarize all of this into one simple statement. Basically, a rapid change in the velocity of the flow rate in the pipeline is going to create a pressure surge. And that can be characterized by a simple equation, Joukowski's equation, that relates change in the pressure to change in velocity. And C by G being the celerity and the gravitational acceleration. And as we are aware, for metallic pipes, the C value in English units is about 3,600 feet per second, or in SI units, about 1,000 meters per second, and G about 10 meter per second squared. So the ratio here would be approximately 100 in SI units. What it means is for every 1 meter per second change in the velocity, potentially there could be 100 meter change in the pressure, 10 bars. Okay, so which is 1 meter per second change in velocity is quite common, and so you would expect a rapid increase or decrease in the pressure to the magnitude of 10 bars, 100 meters, about 300 feet. So because the check valves are trying to prevent the reverse flow, and in the process are going to create some velocity change, it is important to know this fact. Once we are aware of this, we can proceed to designing, sizing the check valve such that we minimize the change in velocity during its operation in preventing the reverse flow, and we can control the pressure surges associated with that. Now, let's, this has been, the check valves, yes, check valves are required to protect the pump stations, but because of, this reason, there have been, many incidents in the past that can be directly attributed to the check valve, where the rapid changes in the velocities have created a rapid increase or decrease in the pressures and the consequent damage to the pump station. And the efforts, the manufacturers are continuously trying to improve on their designs such that the change in velocity would be minimal, while the check valves are trying to prevent the reverse flow. And for that reasons, there are a large number of different types of check valves have been developed, over the years, and let's talk about them briefly. I'm not going to be able to cover all of them, but I'll try to touch upon the most frequently used check valves, most common types of check valves. The common types of check valves are swing type or tilted disc type check valves. This is the most commonly used for a lot of different applications. The extension of this is, you have multi-disc instead of a single disc. We have double disc or multi-disc type check valves. Then we have nozzle type check valves, also referred to as silent check valves or anti-slam check valves. Then there are globe type check valves, ball type check valves, and these are all the commonly used, the types of check valves in the field. And sometimes we may have to work with, when some of these check valves are not suitable, we may have to go with hydraulic actuators for the check valves, and we'll talk about them, in detail towards the end and how to model them as well. So, you may have to have hydraulic actuators, which can be fitted to a normal swing type check valve, or it can even be placed on a butterfly valve. And if that is also not, we also have one other type called control valves as check valves. We can use pump control valves as a check valve as well. We'll talk about that too. So our focus is going to be on these, especially, the swing type and the nozzle type, and then we'll move on to the others later. Swing type, the general construction. You have, if this is a pipeline and the disc is attached to a hinge here, and the flow will be from left to right in this graphic. When there is a flow or a pressure diff, on the pump startup, the disc gets lifted up and stays in this position during the steady state flow, and when there is a pump trip, reverse flow, the disc starts closing, and it will they close completely after some positive time, and thereby preventing the reverse flow. So we have swing type, tilted disc, wafer type. All of these, our general principle is there is a disc that gets lifted up during the steady state conditions, and then it falls down to close the opening here, and thereby preventing the reverse flow. And here is another illustration of how a swing check valve works. So here is a schematic of a swing check valve, and the disc is in its fully open position. Flow is from right to left, from my right to left. This is the flow direction. So there is a flow, and there is enough velocity for this flow to keep this disc in its position right there, fully open position. Here is the hinge that holds this disc in its place. And now when there is a pump trip, the forward moving fluid will continue to move for a few more seconds or a few more minutes, depending on the case, depending on the hydraulics of the system. But eventually, this flow will come to a standstill. And then the reverse hydraulic gradient, higher hydraulic gradient on this side, lower hydraulic gradient on the pump side, the reverse hydraulic gradient will force the water to flow backwards into the, through the check valve. At that time, the disc starts dropping and eventually will close, preventing the reverse flow. Here's an illustration of this. So now the flow reversal, on flow reversal, the disc starts, right at the time of flow reversal, or slightly before or after, the disc is going to start falling, and but the flow reversal continues because there is an opening here. The flow in the reverse direction starts establishing, starting at 0. It may start picking up velocity, and the valve is keeps closing, almost closed, but not quite. There's still passage. That means there is the velocity starts building up, and eventually this is going to stop. They stop the flow. So the disc is completely closed. And then what happens? Just prior to complete closure of this disc, there was fluid flowing in the reverse direction. That means there was an associated velocity. And when the disc closes completely, that velocity comes to a standstill. That flow rate comes to standstill. That means there is a rapid change in the velocity. That rapid change in the velocity, depending on how slow the disc closes or how rapidly the disc closes, the velocity just before the disc is completely closed could be significantly high, and the rapid change of that, the velocity of the flow rate will give rise to a rapid increase in the pressure. And that's what is normally referred to as a hydraulic slam associated with the check valve, or sometimes check valve slam. Not the mechanical slam, it's the hydraulic slam. Mechanical slam is basically the metal touching the metal, the metal disc touching the metal body of the valve, giving a metallic sound. That's not what we're talking about. Here, the sudden, the rapid change in the flow rate from some positive, the finite value to 0, giving rise to a sudden increase in the pressure, and that is what is referred as a hydraulic slam. So what is an ideal check valve? Now that we have seen the process of check valve, swing check valve closing during the flow reversal, we can say an ideal check valve is the one that closes instantaneously on flow reversal. Suppose we have a check valve. We have flow in the positive direction initially, but then the flow reverses. Just at the time of flow reversal, the velocity in the pipeline would be zero. And if we have a check valve that closes right at that instant, the change in velocity would be zero, because the velocity itself through the pipeline is zero. The change in velocity would be zero. That means delta H, the resulting pressure increase, would be zero. That means it's basically a silent closure, and that would be the ideal check valve. But unfortunately, we know very well there is, this is a complex device, and it's almost impossible to close it right at when the flow becomes zero. And that's where the many improvements have been worked out by the manufacturers. There's a lot of R&D going on into this, trying to minimize the change in velocity when the valve is completely closed, which would result in this minimal increase in the pressure. If we cannot have a valve that closes right at the instant when the flow becomes zero, we need to have a valve that closes with the minimum reverse flow just before complete closure. So right at this instant when it is going to close completely, we would like to have minimum velocity, minimum flow rate in the reverse direction, so the change in velocity would be less and consequently very little increase in the pressure head. So how to minimize the reverse flow? Again, talking about the the swing type check valve. If you look at the mechanism here of the actual closure, the valve would be, the disc would be somewhere over here for the steady state condition, and it starts dropping on flow reversal, and it takes some time for the disc to travel from here to this position. And clearly, if we can reduce the disc travel, how much distance the disc need to travel, we will have a shorter travel, means shorter time for the flow to establish in the reverse direction, and less change in the velocity because of that. So it's, we would like to have a disc, that travels the minimum. And what it means is, suppose I keep the disc only in this position during the steady state operation, then it would have to travel only this distance during the transient operation after the pump trip. Compare that with the disc that need to travel from here to here instead here to here. Obviously, this will give very little opportunity for the flow to establish in the reverse direction, and consequently very little increase in the pressure due to check valve slam. But the problem with this is it is obstructing the flow. If you keep the disc in this position for steady state condition, it would be obstructing the flow, create more head loss, and check valve may come into operation once in a day or once in a year, depending on what type of system we are working with and how frequently we turn the pumps off or pump trip condition. Whereas the check valve, the disc would stay in its position all the time. All the time the pipeline is operating. That means more energy loss. Okay, so that's the trade-off. So suppose I have a spring attached to this disc here, and if the forward flow is capable of holding this disc in its position, the velocity, sufficient velocity is required when you have a spring to keep this disc in the fully open position. And on pump trip, the disc is going to, accelerate, is going to push this disc forward a lot quicker than the disc coming on its own. So that will speed up the process of closure and minimizes the chances of reverse flow. It gives less chance for the flow to establish in the reverse direction, and consequently less increase in the pressure because of the check valve slam. Also, you can see if I have low inertia for these moving parts, and that's also going to help. Higher inertia is going to be detrimental. Higher the inertia, the disc moves slowly because of the inertial effects, and gives enough opportunity for the flow to establish in the reverse direction. So there is one misconception here. The swing check valves also have an external lever, and sometimes we add weights to that lever called counterweights, and thinking that the counterweights are going to make the disc to close faster on pump trip. It's really not. It actually makes it worse. The heavier the weights are heavier moving parts, higher inertia, and more time for the disc to close. But it is true that adding counterweights would help reduce the hydraulic slam associated with check valves, but the main reason for that is when you add a counterweight, the disc is not going to be able to open fully to its the full open position. Instead, it may be more like this when the counterweight is added, and when there is a pump trip, it would have to travel less distance. Okay. So, those are some of the ways that you can minimize the reverse flow. The spring-assisted closure, it doesn't have to be only for the check valves. The other types of valves, like nozzle type and globe type, they all use springs, to help them close faster, and that's the reason they can sometimes close very, very, very quickly. The fraction of a second. As quickly as 0.05 seconds. So which means very little chance for the reverse flow and very little pressure increase. The other types of valves, again, like I said, scores of different configurations have been developed by the manufacturers. The sole purpose of all of that is to minimize the reverse flow. For example, here, this is a slanted disc. Here, if this were not there, if this construction was not there, the disc would have to travel from here all the way down here, the vertical. But now the travel is limited to only this, almost half. And of course, the first half of travel is going to be much more longer because there are no forces acting on this disc. But still, it would have to travel much less than it would have, it would have traveled otherwise, thereby minimizing the check valve slam. And the similar principle, instead of attaching the disc, to one end of the disc to the hinge, we can attach the disc right at somewhere in the middle, maybe 2/3 and 1/3. And this would be again, the travel for this is much less. The distance it would have to travel would be much less compared to if it were attached to the top of, the body. And so as you can see, the sole purpose of all these is to minimize the travel time. Here is a dual disc. Instead of a single disc like this, if you put two discs, and on flow, this is the way the flow is going to take place, flow direction. And, during the steady state condition, the discs are in the fully open condition. And during, the flow reversal, the distance they would have to travel is much less, and then consequently very little slam. The extension of that is a multi-door or multi-disc check valve. As you can see, instead of putting one big disc, you put multiple smaller discs. You will have much reduced travel time, and then much better response. The problem with all of these is when you have more number of moving parts and hinges which are directly in the flow, all of these are going to be the practical difficulties that you would have to overcome. And if there are solids in the pipeline, in the water, that's going to be a big problem with these kind of, the check valves. But, as you can see, there have been efforts underway by the manufacturers to reduce the travel time and consequently reduce the pressure surges. Here's a cross-section of a nozzle type check valve. And again, as you can see, there is a spring attached to it. And this, this is a flow direction, and this under steady state conditions, the flow, the pressure forces acting on this disc will keep the disc in open position, and on flow reversal or when the flow becomes zero, the spring immediately pushes this disc forward, keeping this closed. And so, you can achieve the closure times very, very small, 0.01, 0.05 seconds, etc. And another type of valve, Kirloskar type, again, it's a nozzle, and it uses obturator, to help closure, etc. Same principle and same character. Again, it uses a spring. And so, we talked about the nozzle type and the swing type, and the others, just follow. Basically, there have been efforts to reduce the travel time and the reverse velocity. Yeah. When it is difficult to close the valve rapidly, that is within a very short period of time, like less than 1 second, half a second, 0.05 seconds, to minimize the reverse flow, if we cannot achieve that realistically, then we should go with other ways, like we should use methods that allow for controlled closure and prevent hydraulic slam associated with rapid change in the flow rate, at the cost of allowing some amount of reverse flow, but close the valve in a controlled manner instead of the sudden, the change in the velocity towards the end of the closure. We will try to extend the closure a little longer and prevent the hydraulic slam. One way to do that is to attach dash parts to the swing check valves, so they prevent, the dash parts stop the discs from slamming. If you can, make them to stop just, maybe 5% of the flow, something like that. The flow up to that point, increases in the reverse direction, but then when the valve is only open 5%, and if there is enough resistance, the further slow closure of the valve is actually going to decrease the flow rate in a very controlled manner and minimize the hydraulic slam. One can add hydraulic actuators or use the pump control valves, to achieve the same controlled closure or controlled reduction of the reverse flow. Hydraulic actuators is an example. Is a regular swing type check valve, and a hydraulic actuator is attached to the swing, the disc right on top of this. And the hydraulic actuator will control the closure of the swing. It's not, the swing, the disc is not going to open and close dynamically. Instead, the hydraulic actuator will moderate its closure, thereby preventing the rapid change in the flow rate. Here is another example of a hydraulic actuator. There is a lot more to discuss on the hydraulic actuator. You need to have powerful enough hydraulic actuator to be able to withstand the dynamic forces, etc. But that's beyond our discussion for today. Pump control valve, is used very, frequently as a check valve. Again, depending on how the settings are, there may be some amount of reverse flow. It's not completely dynamic. I mean, the check valve is not independent. It depends on the pump controls and the settings on this control valve, which need to be modeled differently. We'll discuss them towards the end. So, again, just to sum up here, the rapid change in the velocity of the flow rate is what creates, very high pressure surges. And if we can come up with a design that minimizes this, that's going to result in safeguarding the pump stations. Now here, the question is, let's go back here. I said, the faster closure means low reverse flow. The question is, how fast is fast? Now, can we get this data from the manufacturer? this is the question that's most frequently asked. What is the software requires the users to put the time of closure, how much time the valve takes to close. Can we get this information? Fortunately, the closure time is not only a characteristics of the type of the check valve, but also depends on the hydraulic characteristics of the pipeline. So if you're pumping uphill, the same check valve may close in certain way compared to if you're pumping downhill or on a very flat terrain. So, it's not, we cannot blame the manufacturers because it's not something that you can get directly. It cannot be something that you can measure one time and then say this is it. So it depends on the hydraulic characteristics. So the manufacturers have been diligently working on this and working with the research institutes to characterize their check valves, and then some of the research has resulted in the characteristic curves like this. A curve, the many manufacturers now provide this type of data, which is the graphs relating deceleration to reverse flow velocity. What exactly it means? Let me see if I have an illustration here. So what they're saying is if we can determine the deceleration of the flow right at the time when the flow becomes zero, and the manufacturers found experimentally what would be the potential reverse velocity when the check valve closes. So I'm using two different terms here. One is the deceleration when the flow becomes zero. Most likely, this is when the check valve starts closing. And it takes some finite time to close. And just before the closure, suppose it takes 1 second, just before the closure, there is going to be potentially some reverse velocity, and this is what that reverse flow velocity is. So if we can give them the deceleration at the time when the flow becomes zero, they will give us the reverse flow velocity. And how can we use this information? If we know the reverse flow velocity at the time of closure, we can use the Joukowsky's equation to calculate what is the potential increase in the pressure of the hydraulic slam pressure, right? So let's move on. And how do we calculate the deceleration? It's very simple. When you run the simulation, and plot the velocity downstream of the pipeline, downstream of the check valve. Suppose in this particular example, I start the pump trip at around 2 seconds. The velocity is 2 meters per second up to that point, steady state, and then it drops. The velocity starts dropping, and eventually it crosses zero. It becomes zero, and then it becomes reverse. This is the flow in the reverse direction. If I can calculate the deceleration right at the instant when the flow becomes zero, and in this particular instance 7 meters per second, I can go to this graph and go to 7 meters per second meter per second squared deceleration, and go to a particular type of check valve here, and then read what is the corresponding reverse flow, and then calculate what would be the expected pressure rise because of that. And if you see some of these graphs, as you can see, this is what is called a straight seat swing type check valve, 90-degree drop, and these are inclined seats. The disc doesn't travel 90 degree, maybe about 50 or 60 degree travel. And if you compare those, for a deceleration of 4.7 meters per second squared, these inclined seat, the check valves give a reverse flow velocity of 0.3 meters per second versus 1.3 meters per second. And if C by G value is 100 times 0.3, 30 meters or 3 bars of increase in the pressure here versus 13 bars, 130 meters of increase in the pressure with, for this particular check valve. So the type of check valves do make a big difference. And look at the nozzle type. Nozzle type almost flat. Doesn't matter what the reverse, what the deceleration is. The expected reverse flow velocity is very, very small. That's because they use reinforced spring, which is very powerful and closes the valve almost instantaneously, irrespective of what the initial flow rate or the deceleration is. And likewise, there are other manufacturers provide this information as well. This is for Kirloskar type. This is a Kirloskar valve. Again, as you can see, irrespective of what the deceleration is, the reverse flow velocity is very, very small. So this is what the industry is moving towards. Irrespective of the deceleration, what would be the reverse velocity? It should have lowest possible reverse velocity. Crane, same way. The swing check valve standard dual disc, just making instead of 2 discs, you have 1 disc. You can reduce the reverse velocity quite significantly for the same amount of deceleration. Another one from Valmatic, the same thing. Ball, you can see, very high. This is by far the worst when it comes to, the reverse velocities versus deceleration. You have swing, other types. From Erhard, many others. These are the ones that I could find, over my practicing, when I do the designs. And I'm sure there are many others, but there are a few that do not provide this information. And sometimes, you could use any of these, and they should have very similar characteristics, and that should be, that should give better idea than not using any of this information at all. Now the question is, how do we make use of this information? Can I put this information directly into the Pipe 2000 software? No, it is not possible because this is the information, non-dimensional characteristic information determined based on flow deceleration and what would be the reverse velocity at the time of closure. So, this cannot be directly incorporated into the Pipe 2000, the modeling. And if we could, we definitely would do it, but, it's not possible to do it. So, this information can be used indirectly to validate your assumption of closing time. You can say, I'm using a closing time of 1 second. Now, whether that assumption is valid or not. I'm going to present an example here to demonstrate what I do to validate my assumption. Here's a pipeline about 25 or 26 kilometers long, 700 millimeter diameter pipeline, about 3 feet diameter. And this is the hydraulic grade. So we're lifting water by about 250 meters here. It's a very rugged terrain, but that's not the point. So here, I want to make use of these dynamic characteristics to validate my assumption of I used like 1 second linear closure for the swing type check valve that was placed in this pump station, and I wanted to know whether that assumption is valid. So what I did for this is, these are the characteristics of the system. I use check valve closure time of 1 second, linear closure. These are the other, the characteristics of the system. So first, I used, I run the analysis, the surge analysis without a check valve, just to allow the flow to reverse the way it is, it can. So I'm not trying to stop. So this is where the velocity becomes 0. An ideal check valve would have stopped the flow right at this point, and the velocity would have been 0 further down. But since I'm allowing the check valve, there is no check valve on this system, flow reverses. But here my intention is to calculate the deceleration. So I calculate the deceleration based on this velocity. It's simply the velocity is meters per second, deceleration meter per second squared. So, you take the difference in velocities between the 2 time steps and divide by that time interval, you get the deceleration, and then plot that graph. So for this particular graph, I'm getting a 7 meter per second squared deceleration. And, for that, from this graph, I read for 7 meter per second, for 7 meter per second deceleration, the reverse velocity is about, for this particular type of check valve, 0.45 meter per second. So, and, using the Joukowski's equation, This is the C value, 0.45, and it gives me a slam pressure, a potential slam pressure of 48 meters for this particular system. And now I did, this is my analysis with the 1 second closure, a check valve, and a 1 second closure. And as you can see, this is the flow rate for 2 seconds, no change in the flow rate, and on pump trip, the flow rate starts dropping. Eventually, it reaches zero flow rate, but since the check valve doesn't close in almost 1 second, the flow continues to reverse and establish in the reverse direction up to this point, and suddenly there is a change in velocity, goes back. This is where the check valve closes, making the flow going from this point to this point zero. And because of that rapid change in the velocity, there is a rapid change in the pressure, which is captured automatically by the software. So the software is telling me there is a pressure spike of 55 meters, and my previous calculation showed me that that particular type of check valve for this system would give me a pressure increase of 48 meters. So my assumption is fine. Okay, maybe I could even reduce this 1 second to a little less than that. Why would I want to do this? This pressure increase is a pressure wave, and it is going to affect the rest of the pipeline system. So I would still have to have a way of modeling the check valve, but then the tools that are available right now are only linear closure and certain time for closure. So that's what I had to do. Okay, now what are the various options available in Pipe 2000 for modeling the check valves? And right now you're familiar with them already. You can put a check valve on a pump element. You can put a check valve on an active valve. And now we added a brand new element, a new element dedicated only for check valve. Now you cannot do anything else with that. It's only a new check valve element. And there are the other options for check valves are check valve with a hydraulic actuator, check valve on a one-way surge tank, zero velocity valve, etc. So the check valves on pumps and active valves, this is the device data that you get when you click on a pump or an active valve. And if you check this box, so that particular element will have a check valve on it. And if you check this box, non-reopening CV, then that particular check, that element will have a check valve, and it doesn't open on, when there is a forward flow again. So like that. And there is yet another option which was already available is CV setting for inertial effects. We'll talk about that in just a second. First, let's talk about reopening type check valves. These check valves, the valve starts closing when flow at the check valve is reversed. That's the assumption. Internal assumption is as soon as the flow through the check valve becomes zero and it is ready to be reversed, that is when the check valve starts closing. Okay, if you put just a regular reopening type check valve. The same is true for non-reopening check valve on the closing sequence. Yeah, and but the same check valve, it also starts opening when the upstream pressure exceeds the downstream pressure at any time during the simulation. So, the check valve starts closing, and it will close in 1 second, 2 seconds, whatever that you set up. But during that process, during the simulation, if the upstream pressure exceeds the downstream pressure, the valve starts opening again. Okay? And, towards the end of closure, just at the end of closure, because of tremendous wave action generated at the time of closure, the pressures could be oscillating back and forth on the upstream and downstream side, and at some one instant the pressure on the upstream side might be greater than the pressure on the downstream side. The valve starts opening and then closes, opens and closes. So this will lead to a lot of check valve chattering when you have just a simple reopening check valve. And the check valves in reality may have a lot more mass to it, a lot more inertia. They don't just chatter the way the model shows. And that's where the difference between reopening and the non-reopening check valve is. A non-reopening check valve will remain closed once it is closed. Once it reaches the closed position, it remains closed. It cannot be open. Now, Are there any such valves? Yes, there may be, but most check valves, you don't have an explicit mechanism to keep them closed after they're closed. But these are suitable for modeling, the way the upstream pressure almost never exceeds the downstream pressure. For example, suppose you're pumping water from, from a very low elevation to a high elevation. Suppose you have 10 meter, 20 meter elevation difference here. And the check valve, whether it is located down at the bottom or even at this location, once there is a pump trip, there is really not much, there is no real chance, for the pressure on the upstream side of the check valve to go above the pressure on the downstream side. So the check valve would pretty much remain, in the closed mode in reality. But in the model, because of the slamming effect, there may be momentary increase or decrease in the pressures on the upstream and downstream side, which may result to check valve chattering. In that case, we recommend you to use a non-reopening check valve. When you have a situation like this and you don't want to see the check valve chattering, a good idea to use the non-reopening check valve. It's also suitable for modeling check valves with high spring constants or heavy counterweights. Again, the check valves, unless they are wafer thin, they will not have a way of opening and closing very rapidly. So we could use again non-reopening type check valve for that as well. And one caution here: when you have a non-reopening check valve at the pump startup, it may remain closed and will not open. And that is there sometimes can be a problem that many users think the check valve is not operating. But if you have it as checked as non-reopening, once it is closed, it's not going to open. Now we did make a small change to the this non-reopening check valve. If the CV is on a pump, not on the active valve, on a pump, then we are allowing the check valve to open when the pump is restarted. You trip the pump and then restart again. We allow the check valve to open. Okay. Now the last one on this, the existing was the CV setting for inertial effects. This is under system data simulation specification, CV setting for inertial effects. Suppose you set this data. What it means is this allows for reducing the CV chattering and the associated spiking. Suppose I set this to 0.1. What it means is once the check valve reaches this 10% closure, okay, it closed all, it moved, it traveled 90% and it is in the 10% range, almost near the complete closure. Then once it reaches that, it continues to close even if the pressure conditions change on the upstream and downstream side. Okay, so this will prevent check valve chattering. If it is some kind of a numerical issue, that can be avoided with this CV setting. Okay, and the same is true during the valve open mode. If you are opening the valve, and again when it reaches, when it is within this 10%, it continues to open even if hydraulic conditions reverse during that process. Okay, again, when this should be tried when checking this option. Non-reopen option is not acceptable for a check valve. You could try this to minimize the check valve chattering, which is much more realistic than making it a non-reopen. Now the data requirements for check valves, we have check valve time and check valve resistance. These are the two important ones that are required for check valve. So the time of closure, CV time, is basically how much time it takes for the valve to go from fully open to fully closed. So I'm going to skip this. And the other one is the check valve resistance. Okay. I do want to stress this point. I've seen many users, have put very small numbers like 0.01, something like that. Now, it's very important to have the right resistance for the check valve. Okay, the reason for that is if I have a very small resistance for the check valve, what it means is until it will not affect, it will not change the flow rate, it will not create enough resistance, it will not, until the valve is closed almost 95%, 99%, and then the last 1% closure is where all the change in the velocity takes place, and that can give rise to very high, the slam pressure in the model, which may not be true in the reality. Okay. At the same time, you don't want to use too much of a resistance because of the same reason. So you want to use the right resistance too, if you want to predict the right amount of, the right kind of pressure spikes that are expected in the pump station. Okay. So this is an illustration that shows, we assume that the flow area changes. Let's suppose you set the time for closure is 1 second. We assume that the flow area changes linearly in that 1 second period. Okay. Consequently, the resistance also changes linearly in the 1 second period. Okay, which may not be true for a given check valve, and that's where we added many other features for this new check valve element. This is a general help screen for the new check valve element. When you go to the drop-down box here under the node information window, you will see a check valve element. And this is the symbol that we used, and this is a general help menu that's available for this valve. I'll go over each one of them a little bit more detail here. These are the new features. It's an independent check valve element, and you can, instead of just a linear closure characteristics, which were previously available, we can have non-linear closure characteristics. And either standard valves or non-standard, user can define the closure characteristics for the check valve. You can also set up accelerated closure. You can let the valve close in an accelerated manner. Initiate the valve closure ahead of flow reversal. You don't have to wait until the valve starts closing, only at the flow reversal. And also a threshold, a differential pressure to initiate the valve opening. Let's talk about these. User-defined flow characteristics. Previously, we assumed the valve closes linearly from, the full open to full closed. And as we know, even for a swing check valve, it doesn't. Initially, there is a lot more inertia for this valve to close, and the forces are not available, not strong enough to make it close. As the valve closes, there is direct force acting on this, pressure forces and otherwise, and which will accelerate the closure. Okay, so the closure will be more likely a non-linear. It's not linear, and now we added the feature to, so the user can define the actual or known closure characteristics. You can either pick the standard valves like the globe valve, under valve type you can pick a globe valve, butterfly valve, etc. And if you just want a linear closure, you just set it to CV ratio or KV ratio option, which will go back to just linear closure. And these are the various options available. A ball valve, butterfly valve will have much better characteristics, but which may not be true for a check valve, so you have to be using caution there. Now, this is where you define the data, for the various standard valves and non-standard valves. You can define the data here, which you're already familiar with. And if you specify for the check valve element an accelerated closure, then, instead of closing the valve linearly or it's going to be closed in an accelerated manner, in the sense it will close slowly initially and then more rapidly towards the end, which is more realistic given the inertial effects of the moving parts of the check valves. Okay, so that can be specified. I have one or two examples towards the end that will show you, what the results look like. So basically, the higher closing speed towards the end, and lower closing speeds to, in the beginning. The another really nice feature here is what is called, you can initiate the valve closure ahead of flow reversal. Let me go back here. So when you have, for example, you have a disc, and it is, and you have a counterweight on it. Let me see, go back here. The counterweight required certain flow velocity for keeping it in its position. Even the disk itself requires certain velocity to stay in its position. As the flow velocity decreases, even in the forward direction, there is not enough pressure to keep this, the forces to keep this disk in its position. The disk may start dropping, okay, which is a good thing because after the flow reversal, right when the flow becomes zero, it has much less distance to travel and gives much better, the response. So we added this feature where you can set up a steady state flow rate. So if for example, if you did the 5 for this, if you added 5 for this value, the CV starts closing when the forward flow rate drops below 5%, not until 0. It doesn't wait until 0. Even when the flow drops to 5% of the steady state flow rate, the valve starts closing, and which may be a more realistic way the check valve closes. The same way, when you're opening a valve, especially the valves with the counterweights and the springs, they may require certain minimum differential pressure across the valves to start opening. The earlier, as soon as the differential pressure is greater than 0, the valve starts opening. Now you have an option to set up a minimum threshold pressure for the valve to start opening. So, in this case, until the pressure differential between upstream and downstream reaches 3 meters or 3 feet, the valve does not open, and it starts opening only after it exceeds that value. Okay. Now, one other thing that I myself am curious about how this characteristics, the stem position versus the flow area and the flow rate changes as the check valve closes. So I added, I'm generating a CSV file, an Excel file that will produce this information for the check valve with respect to time. And this is how it looks like. I have only one check valve and an example with time, the stroke of the valve, and the area ratio available for that particular time for nonlinear closure, and the associated flow rate. And I have a couple of examples to show you here. On one system, I used a needle type valve to model the check valve, and this is the flow rate variation, and the blue line is the stroke, which is changing linearly. The stroke itself, the valve is changing linear. The stroke of the valve is changing linearly in that 1 second, or half a second in this case. But the area ratio changes non-linearly. See, there's a curvature on this, and this is the associated change in the flow rate. There is, the flow becomes negative here, and then suddenly becomes 0, and then there are associated pressure wave actions. Now, when I change this to a butterfly valve, you can see the difference. Instead of the red line being like this, now it is the other way around. Let me go back. You can see the difference. Okay, so these are the new features, and it allows you a lot more flexibility in modeling the check valve. But at the same time, I don't we should not be misusing these features. They are there to better model the features the check valves, but one should find more information from the check valve manufacturers to authenticate the kind of data that you're using, and also use the check valve dynamics to authenticate the closure characteristics, etc. Okay, this is a comparison of a needle valve versus a butterfly valve, the closure characteristics. As you can see, there is a difference. Not much in this particular example, but clearly there is a difference. The blue line is with needle valve, the red line is with the butterfly valve, much better closure characteristics. Okay, now doesn't mean we should use butterfly valve. This is just an option. Okay, so these are all the various options that we added. And I want you to, review these and then give me a feedback and see if we need to add more features along these lines, that we will very certainly entertain. And I think we're almost time here. I think it's past 2 minutes past. So I'm going to stop here. The other things that I have here is you can, probably go through this quickly. Let me quickly go through this so it's available on the recording. So the check valves and the one-way surge tanks, again, we use, whatever we discussed earlier is applicable for this as well. There's a non-return valve or a check valve which closes linearly, etc. Now the check valves and hydraulic actuators, the check valves and the hydraulic actuators. The way to model these is when you have an hydraulic actuator and a check valve, the check valve is not moving on its own dynamically anymore. The hydraulic actuator is controlling the closure of it. So the best way to model that type of check valve is to use active valve. Okay. So hydraulic actuator may be modeled as active valves with user-specified change data to control closing sequence. I did many models on very large pipeline systems. We're talking about 2-meter diameter pipeline, 2-meter diameter check valves. It's very hard to get a swing type check valve of that diameter. So the best way to handle flow reversal there is to have a butterfly valve or a gate valve or some other device there with a hydraulic actuator that opens and closes in a controlled manner. The closing times in some of the models that I worked with are almost like 30 seconds. The first 15 seconds, the valve closes by about 90%, and the remaining 10% is closed in the next 15 seconds. Please note, this particular check valve, the hydraulic actuator is not closing, is not going to wait until the flow becomes reversed, the flow becomes zero. It starts closing on the pump trip. So depending on the type of the system, we have to design the actual closure characteristics, and but the best way to model that is simply an active valve. And make sure you do not check the check valve element box on it, okay? When you model a hydraulically actuated check valves, you should not check the check valve element. It's not a dynamic check valve element, it is actively controlled check valve, so we should not check that in there. I think that's all basically I have. There is another 1 or 2 slides on the the zero velocity valves, but I'm going to pass. Again, thank you very much for your participation.